So the idea of that I'm going to present to you is a work that we developed last year at IC Alps. That is the company that I'm currently working with. That we integrated a security interface of a client that it was like non-standard whatsoever with Tessent MBIST. So the idea here is to give you a idea of how we did that and what's the main points that we take advantage of the Tessent features. So for the presentation today, I'm just gonna test for 5 main topics about who we are in the company, the context of the work that I'm gonna present you, with some details of the DFT structure that we developed, as well as what we did regarding the DFT insertion flow, and then some final considerations. And of course, sorry, just for say thank you Siemens to make it possible to make this presentation remotely. Is the first time that I'm attending the user-to-user event, and as well as to Nicolas Lebron. There was the one that proposed me to present to you today. So first of all, about IC Alps, the company that I'm currently working as a IC physical engineer. We are on-demand IC stock design supply company located in France. In the beginning, we start here in the French Alps and Grenoble. And later on, we expanded to Toulouse with another building with some digital and mostly analog teams. So in the end, we have around 100 experts in the domain. And on top of that, we can provide some services regarding project management. We have an in-house measurement lab if we can measure the chips that we design. We have available application engineers as well as people in the supply chain, and we work in a vast domain of applications as healthcare, automation, industry, and security. So what I have to present to you today, this lovely day, is one of the projects that we worked last year in a security level. So we work in a security design, and we had some DFT demands as usual. As a basic one, we had some memories in the design, so we were obliged to insert MBIST to validate the memories, and scan chains with compression. So in this case, we by default we use Siemens Tessent to make all the insertion and the TPG generation, the pattern generation. The problem is that our client decided to make a small joke in the beginning, saying that they didn't want to use any standard interface whatsoever. So they say, "Oh, you are not allowed to use anything to control the MBIST, nor the compressor or the scan chains." So that's a little bit complicated, but they decided no. But we have an in-house security interface that we developed ourselves, and all the testing features should pass through this interface. So the control and the checking of the MBIST should be done with this security interface, this IC SI, and this CAN interface should only be available after authentication. So to give an overview about this matter, if someone is familiar with the structure of the Tessent MBIST, usually the basics, we have this kind of architecture that we have a JTAG tap that is going to have an external interface that you communicate with the tester or another type of external device. The JTAG tap will communicate with the Tessent MBIST access port that serves as a bridge between the tap and the MBIST controllers that them will be responsible to really generate the MBIST pattern and test the memories and give a result. But in our case, we have a obscure security interface proposed our client, and they said to us, no JTAG, no tap, and you have to use the security interface to communicate with your MBIST. So that brings some issues because in the end, especially because with the pace of the project, we didn't have any information regarding the authentication process of the interface. So it was a little bit complicated to, like, it was not possible to integrate with our test benches, especially Tessent's test benches. And in the end, the full simulation verification was only done by the client's test bench that wasn't available at the time. So the idea is, okay, the JTAG tab should be replaced by the secret block. How to integrate it and how to at least validate somehow with what is available with Tessent in with MBIST and scan. So that's not ideal, but as usual, I have a research background in asynchronous circuits, so we can improvise all the time. So here, I'm gonna try to give you an overview about the architecture, the DFT architecture that we develop in this work, especially with the constraints that the client imposed to us. So the idea is that we have two main points to attack here. We have to configure the MBIST. When I'm talking about, especially about the MBIST, we have to configure the MBIST, and we have to somehow launch and check the MBIST with the security block. So if I start regarding the configuration point, the idea that we start to looking was to try to make the most simple approach to configure the MBIST. So we started thinking maybe we can initialize the MBIST already in a configuration that we can launch it directly without without the need to charge the internal registers of the MBIST or the BAP MBIST. So in the end, we don't have to make any interactions in the beginning with like a JTAG interface. So the idea that we had was to leverage from the default MBIST configuration through the BAP registers, the TDR registers, through someone that usually works with the Tessent MBIST. There is a possibility to configure individually each MBIST controller to see, I want this kind of a parameter for each memory, but there is a possibility to launch globally the MBIST through the BAP BIST. So we just configure the BAP and launch the MBIST. So the idea that we had, so okay, we don't have the JTAG, so maybe we can just modify the RTL of the BAP and initialize the internal registers with the default MBIST configuration. So in the end, we have no need to load the TDRs through JTAG. So in this matter, if we go back to the overview of the MBIST structure, so considering that we have already the MBIST, the BAP configured, so we just need to launch and check the MBIST with the security interface. So maybe we have already our static config values that are already set between the BAP and the MBIST controllers. Now we have to kind of develop a bypass between the BAP and the MBIST that we can use the security interface to communicate and launch the MBIST controllers. So the idea that we had was to develop a custom tiny bypass bridge block that was able to make the bridge between the security interface with the MBIST controllers that we call the BAP bypass bridge, the twin B block. So that one, we give the possibility with the interface, the security interface, to control the MBIST, at least launch it, to monitor if something went wrong or not, and to see if the MBIST already finished its execution. And a brief point about the scan. That part, the client was nice with us because they already provided the security interface already with some integrated logic to to make the bridge between the external scan interface with our compressor and the scan chains. So we just had to wire it and respect the spec of the security interface. So that imposed some quite modifications in the design. So how we did that. So here I'm gonna try to give you an overview about the DFT insertion and verification flow that we did it in this project. So this is an overview, like the beginning when we received the RTL freeze until the execution, the implementation of all the steps, modification of the design for the DFT insertion, synthesis, all the matters just until the place and routing and the final pause layout simulations. So here, for anyone that works with Tessent, usually when we make the MBIST insertion, we have the RTL1 phase that we did. We make the MBIST simulations with the standard Tessent test benches. We didn't make any modifications in this level. After we did the insertion of the ODT, that is the compressor. So is the RTL2 phase. And later on, we made finally our in-house RTL modifications. That there we make the 3B insertion, the block that make the bridge between the security interface and the MBIST. The wiring of the security interface and the suppression of the logic, especially of the JTAG tap. And in this point, we had to perform some adapted Tessent MBIST simulations that I'm gonna detail a little bit later on. And that point is we are ready for synthesis. After synthesis, we have scan insertion, normal scan insertion, ITPG in simulation just to verify that the scan went okay. And finally, PNR place and routing with the final simulations. So here, regarding all this flow, there is 2 points that I want to highlight. Is the possibility with Tessent to manipulate the RTL and modify the design according our demands, and the custom modifications that we did regarding our adapted Tessent MB simulations and scan simulations. So first of all, regarding the manipulation of the design with Tessent, so is the insertion mode. Here we have the possibility with the tool to add and remove logic or sub-modules in the design. Is we can do by explicitly declaring logic cells or sub-modules, or reading directly RTL files and insert in the hierarchy of the design. And of course, we have the possibility to rewire the design. So just to give you kind of like an idea that, like one example, when we were inserting our BAP bypass bridge, here I give you like some examples, like how we bypass the BAP with the rest of the MBIST connection with one of the control signals of the MBIST. We had the possibility to read system verilog file that we develop ourselves. Enter insert mode, create the instance, and after we are able, like for example, to understand how the wire is connected, how is the fan out or even the fan in, and make the modifications according our desire to make possible to integrate our custom block. And regarding that's the more for the manipulation of the design. Just a tiny example. Later on, regarding the test benches, because we didn't have anymore the JTAG interface, it wasn't possible like to use a standard Tessent test bench to interact with the circuit. So the idea that we did here was a really simple approach, was to emulate the behavior of our circuit interface block through simulation forces. On top of that, we added extra top Verilog module in our test benches that were able to check the MBIST results observing internal nodes of our security interface block. And because after some while in the project, we understand that we needed to inject errors and this operation to confirm that the security interface was able to capture a go or no go result. And a final point is that all the simulations run here in this case was integrated with Siemens Questa. So here, tiny example about the behavior of our security interface block to forces. Here I have a bundle of force commands that is provided to Questa, giving details how I want to set some values in some outputs of my security interface block. Like here, the example is like to release the MBIST reset in a given moment, and after launching all the MBIST controllers at the same time. And later on, this a separate file that when I launch Tessent with the run test bench simulations as a native command in Tessent, I'm able, for example, to give a force.do file that are gonna read this file before launching the simulation. So in that way, I can have a kind of like a basic behavior of my security interface block. Later on, about this extra top Verilog module that I mentioned before. Here, even something that you can find in the online in documentation of the Tessent's documentation. It's possible to, with the run test bench simulations, is you are able to give an extra Verilog file that will be put in the top, almost like in the top level of the test bench, that you can use, like for example, to monitor internal nodes of your circuit or even force something in the design. So here we insert a fault injector module that had like 3 main steps during his execution, that we were able to say to him like where and when to inject faults in the design. Like for example, we inject a error or a stacket in the address or even the data of a given memory. After we say to him like how long to wait, or wait a given flag of the MBIST to say that okay, it's done, you can check something, and in the end check expected value of a internal node and give and report it. So for the presentation today, that's mostly all that I want to highlight for you. But before leaving with my final considerations, here in this work, despite the fact that we have quite a lot of incompatibilities between Tessent and the constraints imposed by our client, in the end, Tessent presents itself as a flexible tool to overcome these issues. So in the end, we were able to insert custom DFT blocks and rewire it and validates partially at least what we have done. And on top of that, be able to adapt Tessent to launch custom test benches. So to initialize internal nodes to simulate secure interface, the interface block behavior, and inject the faults to validate the integration between MBIST and our security block. So thank you very much for your time.